So welcome everyone to the CPPC seminar. So today we have again two speakers. Our first speaker is Daohan Wang from the ITP in Beijing. Daohan is about to graduate, about to finish his PhD, and he is working on collider physics, broadly on collider physics and BSM physics at colliders. So today he will be telling us about searching for the axion-like particles at the collider. So please, Daohan.
Okay, thank you very much for your kind introduction. And, thanks for giving me this opportunity to make a presentation in this seminar series. I'm Daohan Wang from ITP CS, and the topic of this talk is about searching for the axion-like particles at collider. And this talk is based on these three papers. And here's the outline of this talk. I will first introduce an overall review of the axion-like particles. Then I will talk about two works about the ALP, and finally I will discuss an ongoing research about axion-like particles and some future research proposal about dark matter. Axion-like particles appear in various new physics models with spontaneous global symmetry breaking, so that their masses and couplings are independent parameters, which is different from the QCD axion. And possible ALP masses and couplings to the standard model particles range over many orders of magnitude. And the ALP searching strategy varies greatly for different regions in the ALP coupling mass parameter space. And the ALP are universal in so many new physics model scenarios, such as the original axion introduced to solve the QCD ECP problem. And it could also be the last pseudoscalars proposed as co-dark matter or dark sector mediators. It can appear in models that have connection with the electron-wake phase transition and play an important role in solving the hierarchy problem. Besides, a generic pseudo-Lamb-Gosson bosons arising from the spontaneous breaking of a new one global symmetry at some large scale, like the R axion, or it can be the pseudoscalar states in the composite Higgs model, or in some models which can explain the mu-2 and or in the cosmic inflation. Besides, it could also be generic pseudoscalars appear in extended Higgs sector as well as in the compactifications of string theory. Well, a considerable region of planetary space of ALP models has already been searched for so many experiments, including the cosmological observations and the low energy experiments and high energy collider. The searches from the cosmology, astrophysics, and low energy collider mostly exploit the Primakov effect, which is associated with the ALP photon coupling. And the collider search for ALP is also predominantly focused on the initial or final state with photons through the such as the photon fusion, or it can decay to a pair of photons to either identify over intrinsically large QCD backgrounds and allow a direct connection with the vast range of all the other existing searches. Therefore, in this talk, we also focus on the ALP photon coupling, and this is the effective Lagrangian. And this lambda is associated with the high energy scale. Is the high energy scale associated with the U1 global symmetry. And here I list some current and future experimental bonds about ALP, including cosmological bonds, astrophysical bonds, LSW experiments, and helioscope, haloscope, high energy collider, and some build-up experiments. And those bold fonts corresponding to the future experiments. Now here I show a current bound of ALP on the planetary space of GA gamma gamma over the MA. And this figure is taken from this paper. And in this talk, we focus on these two mass ranges. The first work lies on 15 GeV to 300 GeV. And then the second work lies on the 0.3 GeV to 10 GeV. Here's a summary of the first talk. I will talk about hunting for top bundle with an axion-like particle signal as the LHC. I will first talk about the motivation and the present model and simulation details. Then I will show some results and conclude this section. Well, a spin-half vector-like top under can arise in composite Higgs model and play the role of regulators of top rule corrections to the Higgs mass to solve the hierarchy problem. And through the mixing with top quark, there are three conventional decay channels of top under. It can decay to a bottom quark and W boson, a top quark and a Z boson, and top quark and a Higgs boson. Current direct search have excluded the mass of top under up to about 1 TeV. And besides, composite Higgs models can also feature an ALP as a pseudo-Namston Goldstone boson from a closable U1 symmetry. And this can decay to the exotic decay channel of top under. They can decay to a top quark and a pseudoscalar. So based on the motivation, we extended the standard model by a top under and a pseudoscalar. And this is the relevant Lagrangian. And we consider both the single production and the pair production. The single production is associated with the electroweak coupling, and the pair production is associated with coupling of top under and gluon. So for simplicity, we only kept the kappa TW and the kappa TA. And for the ALP Lagrangian, we neglected the coupling to the fermions, and then the dominant decay channel will be two gluons. And to enhance the sensitivity, we choose to study a minor but cleaner decay channel, the diphotons. And here I list two cut flow tables of our basic selection criteria for the single and pair production for these two benchmark points. And this is the corresponding standard model background. And from the table, we can see that after basic selection, the cross-section of the background is still about 2 orders of magnitude larger than the cross-section of the signal. So we need to further suppress the standard model background. Therefore, we choose to implement a boosted decision tree for a multivariable analysis. And for single production, we select a series of variables for as the BT inputs. And I show some of their distribution, and which shows good discrimination between signal and the background. Similarly, for the pair production, as we still select another a series of variables. And finally, I show the model independent two sigma exclusion limits on the cross-section as a function of top under mass and the pseudoscalar mass with integrated luminosity of 300 units femtobar and 3000 units femtobar. This is the two sigma exclusion limit on the cross-section. This is the same exclusion limit on the single production. And finally, I show the exclusion, two sigma exclusion integrated luminosity and the branching ratio as a function of top under mass. And we select several pseudoscalar mass. And from this figure, we could see that when the top under mass is larger than 800 GeV to 900 GeV, the single production is more sensitive than the pair production, which means that, which is partly because that the single production has a larger phase space. And here's the conclusion. So in this work, we studied the observability of a new signature of top under decaying to a pseudoscalar through the single production and the pair production. We found that the clean decay channel of diphoton channel helps to suppress the huge QCD backgrounds. Even the branching ratio as small as 0.1%. And we also present the model independent exclusion limits for single and pair production. And these limits can be easily interpreted to concrete model. And we also compare the direct search sensitivity of single and pair channel. We found that the single production process can be more sensitive than the conventional pair production when the top under mass is larger than 800 to 900 GeV. Okay, next I will talk about the second work. This is a summary of the second work. I will talk about utilizing the photon jet method to probe Axion-like particles at the LHC. I will first talk about the motivation and present model and simulation details. Then I will discuss the two methods, and one is the jet substructure variables analysis, and the second one is the jet images. And finally, I will show some results and conclude this section. Well, in the LHC experiment, when the axion mass is larger than 10 GeV, the two photons from ALP decay can be separated enough and identified as two photon events. Well, if the ALP mass is lesser than a few hundred MeV, those photons are highly collimated so that they will be detected as single photon events. Well, between these two mass limits, this will lead to an interesting signature, photon jet HL-LHC, which is a collection of two collimated photons that form a jet-like deposits in the calorimeter. The photon identification at the LHC is based on the electromagnetic calorimeter tower. But for the QCD jet, the identification is based on the jet clustering algorithm. And the current LHC do not search the photon jet signal at all. So in this work, we decided to view the photon as a jet-like deposits. And we cluster photons and hadrons together and into these three kinds of jets. A photon jet, which is a pair of collimated photons. A single photon is only a photon, and QCD jet is it contains several charged hadrons, neutral hadrons. And in this work, we will focus on the ALP that only coupled to the electroweak vector boson with a mass in MeV to GeV range. And there's no ALP coupling, gluon coupling, so that the dominant decay channel will be the ALP-strahlung processes. And this is the relevant Lagrangian up to dimension 5. And now I'll talk about the simulation details. So we use MATLAB to calculate the relevant cross-section and generate singular background events. And these photon level events are showered and hadronized by PCR8. And we also consider the pair events. The solved QCD pair events are also generated by PCR8. And the detector simulation is performed by the Delphis, and the FastJet is used for jet clustering. And in the simulation processes, the propagating particles first create tracks of electrons, muons, and charged hadrons. The electrons and muons identification is based on the default CMS card file. And so only the photons and the hadrons are reconstructed to cluster jets. And based on energy flow algorithm, these photons and hadrons pass through E core and H core and to create energy flow objects. And we clustering these energy flow objects by the anti-KT algorithm with jet radius equals to 0.4. And here I show the basic selection. So since we demand leptonic decay of W boson and Z boson, so the electron and muon identification is used for event selection. And after basic selection, there will be three kinds of jets. The photon jet corresponding to the WA and ZA signal, and the single photon corresponding to the W photon and Z photon background, and the QCD jet corresponding to the rest standard model backgrounds. And we will try to distinguish our signal by distinguishing these three kinds of jets. I will use two methods. The first method is jet substructure analysis. In order to discriminate all these three populations, the following variables will be implemented in the boosted decision tree for multivariate analysis. I will introduce two conventional variables and several unsubjective variables and two substructure variables. Well, the first one is the hadronic energy fraction of a jet. It measures the energy fraction carried by a jet's constituents that belong to the hadronic calorimeter, which is denoted by theta G, and this is the distribution of log theta G for all the signal and backgrounds. And second one is the number of charged tracks in a jet. By counting the number of charged tracks in a jet with PT is larger than 2 GeV, and this is the distribution. Next is the unsubjective variable, which is a measure of the number of energetic subjects inside a jet. The typical procedure is that we take a jet and determine the candidate subject directions by using the exclusive KT algorithm and forcing it to return exactly n jets And given a set of n axes, we can define this variable tau n, in which the k rests over all the constituents of the jet, and the PTK is the transverse momentum of the k's constituent, and delta r LK is the angular distance between the L's subject and the k's constituent of the jet. From the definition, we could see that if a jet with tau n equals 0 has all their constituents aligned with the candidate subject directions, and so it has at most n subjects. But if a jet's tau n is much larger than 0, it will have a large fraction of constituents distributed away from the candidate subject directions, and therefore they will have at least n plus 1 subjects. And based on this definition, we construct the 4 kinetic variables, and this is their distribution, which shows some discrimination between the background and the signal. Okay, the last one is the jet substructure variables. We recast the leading jet constituents using KT algorithm, and we obtain n exclusive KT subjects. We set n equals to 5, and we take the 3 hardest subjects to construct these 2 jet substructure variables. The first one is the fraction of the jet PT carried by the leading subject, lambda g. This PTL is the leading jet's transverse momentum, and the PT jet is the transverse momentum of the whole jet. And second one is the energy correlation function of the 3 hardest subjects. So EI is the S subject's energy, and EJ is the energy of the whole jet. This is the distribution of these 2 variables. And after the construction of these variables, in order to achieve simultaneous separation of the photon jets, single photons, and QC jets, we train 2 BT based on 2 different sets of variables, with the photon jets as signal and QC jets and single photons as background. In the BT1 analysis, the photon jet tends to get a higher response, and QC jet tends to get a lower response. And in the BT2 analysis, the photon jets tends to still get a larger response, and the single photon tends to get a lower response. And we can set a BT response cut to select our signal. And in the 0.3 GeV to 10 GeV mass range, we select 12 signal points, and we try to find the optimal cuts for each point. And based on these points, these cuts, we can obtain the 2 sigma exclusion limits. The second one is the jet image method, which is based on a machine learning technique. We reorganize the information of jet constituents provided by the E-core and H-core as digital images, which are also called the jet images. And in this work, the jet images are of 14 times 14 pixels resolution, covering minus 0.4, 0.4 times minus 0.4, 0.4 in the eta phi plane, centered around the jet axis. And 0.4 is just the jet radius in our analysis. And for each pixel, we construct 4 separate image channels, and the pixel intensities in each channel corresponding to the averages of the transverse momentum separately. The first channel is the average of transverse momentum for all the particles. The second channel is the charged hadrons. The third channel corresponds to the photons, and the fourth channel corresponding to the neutral hadrons, falling into each pixel over the total number of the events respectively. And here is the jet images of these 3 kinds of jets, which shows some discrimination. And we will design a convolutional neural network to try to distinguish these 3 kinds of jets. And this is the architecture of this convolutional neural network. The input is a jet image of 14 times 14 pixels with 4 channels, and after an attentional module and several convolutional layer and pooling layers, we can finally obtain feature maps. And we flatten this feature map into a single vector and feed it into a fully connected neural network. with 2 hidden layers. And finally, at the output layer, we use the softmax activation and to generate 3 classes probabilities. In other words, if a jet picture is input, and the output will be the 3 probabilities that this jet is tagged as a photon jet, a single photon, and a QCD jet. The sum of the probabilities is 1. Here's the parameter setting of the CNN. We choose the cross entropy as the loss function. And the CNN is trained using the Adam optimizer with a constant learning rate of 0.001. And the CNN were implemented in the deep learning framework of PyTorch with GPU acceleration. Here's the ternary plot of the results. The red, green, and blue points corresponding to the photon jet signal, single photon background, and the QC jet background. And the projection of each point on the 3 edges corresponding to the probability. And after jet tagging, we should build another simple neural network to learn an optimal selection cost on the jet tagging probabilities, since the significance depends on the event selection efficiency. So the input will be the results of the CNN and will be 3 classes probabilities, and the output is a number between 0 and 1. And in order to estimate the statistical error, we trained 7 selection neural networks to obtain the mean significance and its standard deviation. And since the neural network is designed such that the loss function is as small as possible to optimize the model parameters, so we take minus significance as the loss function, which means that the neural network will try to make the significance as large as possible. And here I show the optimal cuts performed by this selection neural network. This black dashed line will be the cuts, and the lower left corner, the points in the lower left corner corresponding to the remaining photon jet events, single photons and QCD jets after the optimal cuts. And after the optimization, we take 0.5 as the selection threshold. So for the selection neural network, the output, if the output is larger than 0.5, we will take it as a photon jet. If the output is smaller than 0.5, we will take it as a background. And we count the number of these 3 kinds of jets that are tagged as a signal and use the Poisson formula to accurately evaluate the detection significance. And finally, we obtained the 2 sigma exclusion limits on the G gamma gamma versus MA. And the red line and the red dashed line and the blue dashed line correspond to the PP2WA and PP2ZA processes based on jet substructure method. And the red band and the blue band corresponding to the PP2WA and the PP2ZA based on convolutional neural network. And since we trained 7 selection neural network, therefore we have a mean for the CNN method. We have a mean significance and the standard deviation, and the band width is about 10 standard deviation. Finally, is the conclusions. Since the 2 photons from the Axion-like particle decay are not well separated for such a large ALP, we performed 2 methods with jet substructure techniques and jet image techniques to successfully discriminate our signal from standard model backgrounds. And with the help of EEG and techniques, we obtained the 2 sigma bonds on the ALP photon coupling G gamma gamma as a function of MA in the mass range of 0.3 GeV to 10 GeV at the 14 TeV high luminosity LHC. And we extended the current LHC sensitivity, and our results are stronger than those from the current BL2 and other studies. Okay, finally, I will discuss the ongoing research about ALP. And in this project, I worked with Professor Bhaskar Dutta in Texas A&M, Professor Yongchao Zhang in Southeast University, Professor Liu in Nanjing Normal University, and my supervisor, Professor Jimmy Yang. This project is based on the dark matter experiment, which is a beam dump experiment for light dark matter detection, and they assume the dark photons could be produced radiatively when by an impinging electron beam on a heavy target nucleus by Bremsstrahlung processes, and this dark photon could decay to a pair of dark matter particles, and these dark matter particles could be detected in this shielded detector downstream the beam dump, and by scattering with the electron or the proton. And in our project, we assume the Axion-like particles could also be produced radiatively through the Bremsstrahlung processes, and it could also be produced through the Primakov processes by the interaction of the Bremsstrahlung photons and the virtual photons from the electrostatic field of the heavy target nucleus. And this produced ALPs could go through the concrete walls and air and reach the detector. And they can be detected through the inverse Primakov processes, or it can be detected through the Compton scattering processes. Finally, some outlook about dark matter. In future, I would like to search for sub-GeV dark matter in high-intensity beam dump experiments and underground direct detection experiments. And I would like also to explore the impact of current dark matter limits on Higgs physics, such as through the loop correction on the Higgs-Ricardo coupling, and cosmology, such as the gravitational wave detection in a first-order phase transition triggered by a scalar potential in various dark matter models. And besides, I would like to also investigate more advanced machine learning techniques to search for dark matter signal, including event detection and anomaly detection. Okay, that's the end of the presentation. Thank you for your attention.
Mikael, I think you muted.
Yeah, so sorry. Thanks, Archer. Yeah, so thank you very much, Daohan, for a very nice talk, very comprehensive. So we have time for some questions. Who wants to go first? Maybe while you're thinking, I can start. So can you go back to slide 39? Okay. So there you looked at the, exactly, 37 as well. Okay, so here you had for the significance, detection significance, you used Poisson's formula. But before, for the optimization, you used just signal over square root of background. But why don't you use Poisson's formula there to optimize directly, or?
Sorry.
Yeah, I'm basically just wondering kind of that. So here you use that simple detection significance
yes,
to optimize it. And then later on, you use the Poisson formula for after optimizing it, you use that one. Was there a specific reason for it, or?
Oh yes. So for the loss function, we first we don't know before the selection neural network, we don't know after the cuts how many signal and backgrounds are left. So we have to make a approximation, and we sum all the probabilities and over all the events numbers as the selection efficiency, and we take them to calculate the significance. And well, we try to use the Poisson formula before, but the result is about how to say, the result is results change vastly. At some points the result is very good, and at some point the result is very bad. So when we choose this simple detection significance, and the problem will disappear. But we don't know why. Yeah, maybe it's the loss function. Maybe the loss function should be differential.
So that it had to be well behaved, and
yeah,
so the
we
logarithms
thought
yeah.
it's maybe because the loss function should be differential. Yeah.
Okay. That makes sense. Any other question?
Daohan, maybe I'll have a very quick question. If you motivate the collider signatures of ALPs from the various theories, and also you provided the certain signatures of ALPs at collider signatures in a fairly model independent way, as I understand. Have you compared this, the axial, the signatures which you've obtained with the potential constraint within the specific well-motivated models? For example, 2 Higgs doublet model, where you can have this axial particle as well. Have you done that analysis as a question? So how your results will fit into the particular models? I'm just kind of inverting your. So, for example, if I want to exclude R axion, how do I read those results that you have in supersymmetric theories? Is that difficult, or yeah?
Yeah, you mean the photon jet, right? You want to take the photon jet signal?
Yes, for example. Yeah.
Okay, I see. So yeah, let me change this. Yeah. So why do we choose the reason that we choose the ALP-strahlung process is complicated, since that we need to take the photon jet away and try to study the probabilities of this substructure jet. And we want to try other processes, such as the vector boson fusion, and the final state will be a photon jet and 2 QCD jets. However, if I treat the photon as a jet, I cannot choose the red photon jet from the other 2 QCD jets. So this method is very specific. So it must demand that the final state must contain a photon jet and other things that such as the electrons, but or muons. It could not the final states could only have 1 jet. If there are more than 1 jet, this method cannot be used.
Okay, thank you very much. It was very nice talk.
Yeah, thank you.
Okay. Any last question?
Yeah, I was going to ask. So I mean, when you were making this plot of the projected constraints for the photon coupling, I see here you also have these couplings to the electroweak gauge bosons. I mean, what values do you set for these CBB, CWW in that plot? How do I understand? Where do these numbers come from? Are they just order 1 or what?
Oh, okay. In our analysis, the FA is set to 1 inverse TV, and the CPP is and CW is just dimensionless number, and in this exclusion figure, and we just set FA equals to 1 inverse TV, and we set the CPP equals to CWW, and
so wait, where does this photon coupling come from? Because does it come from like the is it some combination with the Weinberg angle or something?
Oh, I see. So I didn't show the. Sorry, could I open the paper? Sorry. Wait a minute. Yeah, this is the G gamma gamma coupling. Yes, and we set CPP equals to CW. And it, yeah.
Okay. Yeah. No, there's no point in it. I should just read the paper.
Yeah,
We go get into more details on that. Thank you. Thank you.
Yes.
Okay. Thank you very much, Daohan. A very nice talk.
Okay.
So I think in the interest of time, we should now